In Chapter 5, the focus was on how to make alkenes. Chapter 6 here is just the opposite. Once we make the alkenes, what can we do with them? Addition reactions are the opposite of elimination reactions. With eliminations, you're losing some atoms from a molecule. With addition reactions, you're adding new atoms. And we talk about addition as being across a carbon-carbon double bond. So we want to be able to predict the outcome of such reactions. If we do a particular addition, can we draw the structure of the resulting product if we know which alkene we're starting with? So here's the general reaction. Y and Z are sometimes identical atoms, and they can also represent groups of atoms. And you can see I've color-coded this one on the screen there to kind of let you match up the atoms with these different examples. The last one there, hydration, is adding water across a double bond. So a new hydrogen appears at one of those carbons and a OH group appears right next door. And as it says, there are many other examples of this, although predominantly we're going to focus on these kinds of examples. Adding hydrogen halides across the double bond, or adding halogens themselves, 2 chlorines, 2 bromines, and certainly creating alcohols by adding a water molecule. That's how you can get an OH group into a molecule that doesn't start off that way. Alcohols, as we've already seen, they're very important. You can do lots of things with alcohols, and one way to make them is to start with a corresponding alkene. And the nice thing about these reactions is that we can be sure about which carbons are modified in the molecule. You can have an alkene with dozens of carbons and other atoms as well. But it's where those double bonds are, that's where the action is. This slide shows the simplest case of an addition called hydrogenation. We just add a hydrogen atom on either end of the double bond. That turns an alkene into the corresponding alkane. And you can see not only does H2 get involved, but on the top of the arrow here, those are the symbols for some metals that would be in powder form. PT is platinum, PD is palladium, nickel, rhodium. In their powdered forms, these are catalysts for these reactions. They just simply make them go faster. And so in addition to hydrogen gas, you would typically use one of those metals to make these reactions go faster. You may recognize the word hydrogenation if you ever read labels on packaging, because some snacks we eat, potato chips, crackers, things like that, sometimes the label will talk about them being hydrogenated or partially hydrogenated. It has to do with taking molecules like this one at the bottom, this long chain carboxylic acid that's also an alkene, and adding hydrogen across the double bond there, turning what's a cis alkene into a regular saturated hydrocarbon. And sometimes you have multiple double bonds along a very long carbon chain, and you can selectively react just some of those. And when you do this, you take things that are oils. If they have double bonds, they tend to be liquids at room temperature, and you turn them into solids. And when an oil becomes solid, we call it a fat. And so that can modify the taste properties and just the general integrity of food when that's done. And so that's a real-life example of hydrogenation. Here are examples of adding a hydrogen and halogen at the same time. And so HBr and HCl both do this. As you can see at the bottom, HI, the iodide, is also good at doing this. HF, not very reactive at all. And so you can see we get a new hydrogen in the molecule, and next to that we get a new halogen. And for both of these alkenes, it doesn't matter which side of the double bond you put the halogen and which side you put the hydrogen, you get the same product. But as we'll see, sometimes it does matter where the halogen goes and where the hydrogen goes. It really just depends on the structure of the alkene that we're starting with. But each of these can only give one unique product. We're going to see a lot more of the examples of these things though.